Geophysicists find a link between seismic waves called PKP, precursors, and strange anomalies in Earth's mantle, according to the University of Utah. For the decades since their discovery, seismic signals known as PKP precursors have challenged scientists. Regions of Earth's lower mantle scatter incoming seismic waves, which return to the surface as PKP waves at different speeds. The precursor signals which arrive ahead of the main seismic wave that travels through Earth's core has remained unclear, but researchers led by University of Utah geophysicists sheds new light on this mysterious seismic energy. PKP precursors appear to propagate from places deep below North America and the Western Pacific, and possibly bear an association with ultra-low velocity zones, thin layers in the mantle where seismic waves significantly slow down, according to the research published in AGU Advances. These are some of the most extreme features discovered on the planet. We legitimately do not know what they are, said lead author Michael Thorne, a university associate professor of geology and geophysics. But one thing we know is they seem to end up accumulating underneath hotspot volcanoes. They seem like they may be the root of whole mantle plumes giving rise to hotspot volcanoes. These plumes are responsible for the volcanism observed at Yellowstone, the Hawaiian Islands, Samoa, Iceland, and the Galapagos Islands. These really big volcanoes seem to persist for hundreds of millions of years in roughly the same spot. Thorne said in previous work he also found one of the world's largest known ultra-low velocity zones. Thorne said it sits right beneath Samoa, and Samoa is one of the biggest hotspot volcanoes. For nearly a century, geoscientists have used seismic waves to probe Earth's interior, leading to numerous discoveries that would not be otherwise possible. Other researchers at the university, for example, have characterized the structure of Earth's solid inner core and tracked its movements by analyzing seismic waves. When an earthquake rattles Earth's surface, seismic waves shoot through the mantle, the 2,900 kilometer thick dynamic layer of hot rock between Earth's crust and the metal core. Thorne's team is interested in those that get scattered when they pass through irregular features that pose changes in material composition in the mantle. Some of those scattered waves become PKP precursors. Thorne sought to determine exactly where the scattering happens, especially since the waves travel through Earth's mantle twice, that is, before and after passing through Earth's liquid core, outer core. Because of that double journey through the mantle, it's been nearly impossible to distinguish whether the precursors originated on the source side or the receiver side of the ray path. Thorne's team, which included research assistant professor Surya Pachai, devised a way to model waveforms to detect crucial effects that previously went unnoticed. Using a cutting-edge seismic array method and new theoretical observations from earthquake simulations, the researchers developed, they analyzed data from 58 earthquakes that occurred around New Guinea and were recorded in North America after passing through the planet. And Thorne said, I can put virtual receivers anywhere on the surface of the Earth, and this tells me what the seismogram should look like from an earthquake at that location. And we can compare that to the real recordings that we see. We're able to now back project where the energy is coming from, he said. Their new method allowed them to pinpoint where the scattering occurred along the boundary between the liquid metal core, the outer core, and the mantle, known as the core-mantle boundary, located 2,900 kilometers below the Earth's surface. Their findings indicate that the PKP precursor likely come from regions that are home to ultra-low velocity zones. Thorne suspects these layers, which are only 20 to 40 kilometers thick, are formed where subduction tectonic plates impinge on the core mantle boundary in oceanic crust. What we found in these ultra-low velocity zones do not just exist beneath the hotspots. They're spread out all across the core mantle boundary beneath North America, Thorne said. It really looks like these ultra-low ULVZs are getting actively generated. We don't know how. But because we're seeing them near subduction, we think mid-oceanic ridge basalts are getting melted, and that is how it's getting generated. And then the dynamics is pushing these things all across Earth, and ultimately they're going to accumulate beneath the hotspots. The dynamic is pushing these things all across Earth, and ultimately they're going to accumulate against the boundaries of large low velocity provinces, which are compositionally distinct continent scale features beneath the Pacific and Africa, according to Thorne. They may additionally accumulate beneath the hotspots, but it's unclear if these ultra-low VZs are generated by the same process, he said. Determining the consequences of such a process will have to wait for future research. So they're always finding new things in geology. This is from the University of Utah by Brian Maffley on phys.org. Please leave your comments, and thank you for your support. Finally, support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below.